Let's start today. Okay, and as I said today, guys, it's it is going to be at the same time very exciting and at the same time very sad because today it's sad that we are leaving trigonometric functions behind. We are moving forward with new concepts, and that's what it makes it exciting to learn a different kind of the functions in trigonometry. Then that's going to be a brilliant thing that we're going to learn in terms of, I should say, uh, the course which we're going to have. Something new, something more exciting, and that's sad. Maybe that we are leaving trigonometry functions behind, moving towards some other stuff. Then. Okay, but before we start, to wrap up, I should say, our lesson for the trigonometric functions, we are moving towards, I should say, something new, which is not going to be new for us, as you know, that this week we are just entering the mathematical modeling challenge, international one on May the 7th. We are going to enter that, May 7th, 2020. And we watched a video yesterday, it was the first part of the 3 videos which we have in order to shape your mind in terms of what is a modeling, a mathematical modeling, specifically for Rose, that she's entering into that challenge. And today, before we start our uh, the final revision on the mathematical modeling, I'm gonna to share my screen with you to watch the second out of 3 videos which I have prepared for you for a mathematical modeling. It's around 2 minutes and a half. I'm gonna share my screen with you. You watch that video, then we come back to talk about that and start our lesson for the trigonometric function, the very last chapter. Okay, I'm gonna share my screen. Oh, this is my screen?
Yes.
Yeah, nice. Okay. And now, and let me know if you can hear the background music or the voice, the volume is loud enough. I'm just gonna play it. So can you hear that? Listen again.
Yes.
Awesome, awesome, thanks. Guys, also, and Rose, also you please take some notes, because from this, I should say, from this video, they are talking so briefly about some strategies that you need to adopt when you just do a mathematical modeling then I'm gonna work more towards those kind of stuff with you before the challenge, but it's good to take some notes then from this video then. Thank you.
Modeling is a process that uses math to represent, analyze, make predictions, or otherwise provide insight into real-world phenomena. Just as there are many ways to do math when modeling, there are many ways to approach your question. So as you begin the process, the first step is critical. Define the problem statement.
Defining the problem is really important because it gets you to understand what you're actually trying to solve and spell it out, just so that you know what to plan for.
The way the problem is worded is not a question. They just give you, information, and you have to be able to pull out what the actual question is and what you're searching for. So you have to define before you can start doing any of the work.
For example, let's say you've been asked to rank roller coasters according to their thrill factor. What exactly does thrilling mean? Max G-force? Length of drop? Top speed? These are all decisions you need to make.
When you define a problem, you actually are finding some of the consisting factors in your problem. So factors that are going to affect your outcome.
If you really take the time to read aloud the entire problem word by word to your entire team and make sure your team really has a grasp of what they're doing, that's going to set them up really well for the rest of the competition.
Remember, mathematical models answer open-ended questions, the kind of questions that are all around you. They can be approached from many different ways, so get creative. Here are a few guidelines. A concise restatement of the problem will tell you what your model will measure or predict. Focus and define subjective words like fast or thrilling. Explore the problem with research and brainstorm. Brainstorm like you have access to any and all data you may need. It's a good idea for one member of the team to record every idea. You never know what you'll need later in the process. Visual diagrams can be a powerful tool to help structure your model in upcoming steps. Keep an open mind. You can prune out unrealistic or useless information later. The math modeling process contains all the ups and downs of your favorite roller coaster. Defining the problem up front will help you focus on the next steps in the process. So sit down, put on your thinking cap, and enjoy the experience. For more information on the math modeling process, visit m3challenge.siam.org.
Okay, it was the second part of the movies that it was a kind of a very brief introduction, the process for the mathematical modeling, specifically when you start to define the problem and find the informative measures and metrics that defines your model, then simplify that to move on then. Yes, Rose, wasn't that interesting?
Yes.
Yeah, did you take some notes?
Yes.
Awesome. Are you sure you took some notes? Because you said yes.
Yes.
Yeah, no worries. I'm gonna also today, I'm gonna give the link to all these two videos on the course website. Then in case if you want to watch it more, then you have the link that during the Saturday and Sunday to revisit the links and watch it once more then. Okay?
Okay.
And now, the thing which we want to do is this. Is that I'm just going to put my laptop upside down and start the day. Oh, these are the notes from the previous class. I forgot to just... Guys, any questions from yesterday, in case if you have?
No.
Nothing? Okay, now let's get it started. As I said, this is the final day of our journey into the trigonometric function. Oh, now just we are gonna move on and make some plans. Okay, everyone is ready now?
Yes.
Okay. Now, guys, the thing that we are going to cover today is fundamentally very interesting, but at the same time, it's going to be very relevant to any other discipline that you work with, probably. At the end of the day today, I'm going to give you an example, and that example shows that how you can just apply those concepts into the, let's say, the real world. The thing that we're going to cover today is going to be this. If you remember yesterday, when we were talking about the trigonometric identities, we discovered, I should say, the two important ones. We talked about the first one, which it was cosine of alpha plus beta. Guys, can you see what I'm writing? I mean, in terms of the light,
Yes.
it's good enough. Okay. We talked about, I should say previously, in terms of, for example, what is a cosine of alpha plus beta, and we've worked too much around it. But we know that in terms of expanding this identity, we know that it's going to be the cosine of alpha, cosine of beta, minus sine of alpha, sine of beta, correct? And also, we had this identity that if we can just write, for example, the cosine of alpha minus beta. You see clearly what I'm writing? You have no problem to read what I'm writing?
Yes.
Is it fine for everyone? Yes, Rose?
Yes.
Uh-huh. Okay, then we talked about the cosine of alpha minus beta. We said that this identity becomes essentially exactly like this, but with a minor difference, which that minor difference plays a huge significant role. We said that it becomes cosine alpha, cosine beta, plus sine alpha, sine beta, right? Okay. Now, guys, I want to ask you, please, find this identity. I want to ask you, please, add these terms together and let me know what is your end results. What do I mean? I mean that what is going to be the cosine of alpha plus beta plus the cosine of alpha minus beta. What is going to be the end result? You please take 2 minutes, less than 1 minute, to understand if you add these two terms together, what is going to be the final result. I think 1 minute should be fine then. Yeah, give it a try yourself. Write these two identities and sum them together. And please let me know when you're done. Are you done?
Yes.
What is your result, Rose?
2 cosine alpha multiply cosine beta.
That's right. Everybody else is done? Gloria and Philip?
Yes.
Yes, Gloria. How about you, Philip? Philip? Maybe he stepped a little bit for a couple of minutes away from the laptop. But as Rose said, and Gloria find that, then when you add them together, what do you get? You get 2, because these terms are going to be vanished. Then you are left with 2 times of cosine alpha, cosine beta. That's right. In a sense, I can rewrite this expression in a different way. And I say that I can rewrite this like this manner. I say that I'm going to isolate cosine alpha to the other side, and I write cosine alpha cosine beta equals to what? I have to divide both sides by 2, becomes 1/2. then becomes cosine of alpha plus beta plus cosine of alpha minus beta, right? And this, we call that our identity number 1, which we derived it today on the May 1st of 2020. It becomes one of the identities. I'm going to talk about what is the significance of this one. What is the relevance of this identity? Look at this one, guys. On the left side, I have cosine alpha, cosine beta, which you see that they are the product of the cosine ratio of two angles then. This is cosine alpha, this is cosine beta. And as you will see, these cosines, cosine alpha, cosine beta, it becomes, when you expand it to the right side, it becomes the sum of two cosines, cosine of alpha plus beta and cosine of alpha minus beta. And that's the significance of this identity, that we say that the cosine alpha, cosine beta, if they are the products, which it means that they are multiplied, they can be expanded in a way that they are written as the sum of these angles. You see? For example, I'm going to give you an example which you are going to use this identity that we learned right now. Imagine that as an example, I'm giving you this, the cosine of (7x) divided by 2 times cosine of, let's say, 3x divided by 2. Look at these two products. Look at that. I have, for example, the cosine. Everybody sees what I'm just pointing at?
Yes.
You see that the cosine of an angle, which is 7x divided by 2, and cosine of the other angle, which is 3x divided by 2. X can be anything. X is an integer number. It can be 0, can be 1, can be 2, anything. Then you see that. Essentially, what did we mean was something like this. We look at this one as alpha and this one as beta. We call that 7x divided by 2 as an alpha, and we look at 3x divided by 2 as beta. Okay, look at this. I compared that with the identity which I derived it now. It shows that if the product of two ratios, and by the product, we know that we mean the multiplication. The things get multiplied into each other to produce the product. We say that if the product of two ratio is both the cosine, which is cosine of one angle, into cosine of the other angle, you can represent it with the same nature into the sum, a linear sum of two cosine angle. You see, that's the product, and that's the linear combination of two. A combination because this is a plus in between them. Then that's the thing. Then as a result, in order to solve this, I'm going to come here and write it in this way and say, then based on the things which I know, it becomes 1 over 2. Do you see this color? Do you see this green color?
Yes.
Yeah? Becomes 1 over 2 of what? Of, it becomes the cosine of the sum of these angles, alpha and beta. It means alpha, this is 7x divided by 2. Beta is 3x divided by 2, which becomes the cosine of, if I add them together, alpha and beta, what do I get? Seven x divided by 2 plus 3x divided by 2 becomes how much? 10x divided by 2, right? plus cosine of their difference, 7x divided by 2 minus 3x divided by 2 becomes how much? 7 minus 3 becomes 4, huh? 4x divided by 2. And there it is. And that's our example. You see, I started from the left with the product of two cosine ratio of two different angles, but on the right, I have the linear combination of two sum of the angles, sum and difference of the angles. I hope you get that definition. Is it clear for everyone?
Yes.
That's right. Any questions?
No.
No? How about Philip and Gloria?
No.
No? Okay. And now, then we move on to the next one. Then the next one, it becomes this, the next identity. I'm going to do the same thing exactly. I'm going to write the same expressions which I have. I mean, in terms of the cosine of alpha and beta. I'm going to write the cosine of alpha plus beta equals to what? Cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. Okay, and now the same thing for the cosine of alpha minus beta. What it becomes cosine of the alpha, cosine of the beta, but this time with the plus sign in between. Sine of alpha, sine of beta. Clear for everyone?
Yes.
Nice. And now the thing is that now, then I say the task which I have is this. The strategy is this, that I just want to, previously I add them together. When I added these two expressions together, it was very natural to see the terms which they include sine alpha, sine beta, because they are one expression and they have plus or minus in between, they should vanish because they are exactly the same value, but with the opposite sign. And that was the reason I got 2 times of the cosine alpha, cosine beta. But the strategy which I have right now is this. I want to right now do some kind of manipulation that I get the terms which they include cosine to vanish. And instead I get an expression in terms of the sine alpha, sine beta. How can I do that? Can I say, in terms of this, can I say if I write cosine of alpha minus beta minus cosine of alpha plus beta? Guys, please you take a couple of minutes, couple of seconds, I should say. Do it yourself to see what the value you get if you take cosine alpha minus beta minus cosine alpha plus beta. You take a couple of minutes to see what you get at the end and what's the end result. Okay, are you done, guys?
Yes.
What do you get?
2 sine alpha sine beta.
That's right. How about Philip and Gloria? Do they get the same thing?
Yes.
How about Philip? Okay, then what do I get from this? It's going to be this one. I'm trying to express the product in terms of the sum. Then it means that I write here sine alpha sine beta equals to, if I divide both sides by 2, I get 1 over 2 of cosine of alpha minus beta minus cosine of alpha plus beta. Okay, let me highlight this around. It becomes our second identity that we learned today. Because identity number 2. And as you see again, what happened here, it's very clear to see that I had a product of the sine of 2 angles. On the left, you see that it can be represented at the same time without loss of generality with the linear combination of 2 cosine function. These two are the same thing, but they have a different way of being represented to you. Alpha and beta can be represented by the sine alpha, sine beta, which they are essentially the same if you just linearly combine them by 2 cosine of their sum or difference. Does it make sense? They are essentially two sides of a one coin. Okay, guys, any question?
No.
Any questions, guys? No? Okay, now I'll give you one example in order to understand what did we deal with. Imagine that we have sine of 15x divided by 2 times sine of 9x divided by 2. Okay, you see that again here, the same thing is valid. You see that you have essentially 2 sine, these two trigonometric ratio, which you can represent them as what? As 1 over 2 cosine of their difference. You can think of 15x over divided by 2 as alpha and 9x divided by 2 as beta. Then you will see, guys, that this function, if you look at this function as the sine of these two products, then you can write it as the linear combination, which is a kind of a manipulation which you do with the trigonometric function. Becomes now the difference of them, alpha minus beta becomes 15x divided by 2 minus 9x divided by 2 becomes how much?
6x over 2.
That's right, 6x divided by 2. You can simplify that further, write 3x minus 1 over 2. I expanding 1 over 2 inside, it doesn't matter. You can just factor this out. I cosine of, if I add 15x divided by 2 plus 9x plus divided by 2 becomes how much?
24x divided by 2.
That's right, 24 divided by 2x. Then you see that this second identity, it allows you that if you are given a function which is the product of two signs, depending on the application that you're working with, you write it as a linear combination of two ratios. Makes a big difference sometimes in the application that the product of two sine function, if your function is given like this, to be decomposed into the linear combination. Yesterday also we learned another decomposition that we just started with the higher power. Then we just learned some power reducing techniques to reduce the power going all the way to the power 1. And now this is the second type of, I should say, decomposition of the trigonometric function, that you start with a product, you decompose into a linear combination. Becomes the second type of the decomposition so far that we learned. Any questions, guys?
No.
No? Okay. Okay, now we move on to the third identity. Okay. Okay. Now we move on from the cosine functions. Is Philippe here? Philippe, are you there?
Yes.
Okay. Philip, do you remember this identity that the sine of alpha plus beta, how did we write it? If you just wanted to expand it for those two angles. Philip? You mean that you just wanted to write the sine alpha, cosine beta, minus sine beta, cosine alpha, plus. Right, Philip?
Mm-hmm.
And also, we had sine alpha minus beta. What is that, Gloria? Gloria, are you there?
Yes.
How do you expand that identity? Rose, do you mean it becomes sine alpha, cosine beta, minus sine beta, cosine alpha? Yes, Gloria? You just want to say that? Gloria?
Yes.
You wanted to say the same thing?
Yes.
Awesome. Okay, and now, what's the plan now? What happens? I just want to give this exercise to Gloria and also to the rest. That what happens if I say, if I add these two expressions together? Essentially, what do I mean? I mean that if I write sine alpha plus beta plus sine of alpha minus beta. What happens if you add them together? Please do that take a couple of minutes and try it yourself to see what is the end result. Anybody's done?
Yes, is equal to 2 sine alpha cosine beta.
Fantastic. Becomes 2 sine alpha cosine beta. Philip and Gloria, you got the same answer?
Yes.
How about Philip?
Yes.
Awesome. Then it means that when you have, if I divide both sides by 2, I get what? I get sine alpha cosine beta becomes 1 over 2 of sine alpha plus beta plus sine of alpha minus beta. Which it becomes our third identity that we are going to learn today before we head for the break. It's going to be our third identity. And you will see that if you take a look, that you see that if you have a product, which is sine alpha cosine beta, which is a product, it is essentially can be decomposed into a linear sum of 2 sine functions of their sum and difference of the first angles then. Correct?
Yes.
Then this is going to be the third identity that we are going to learn. But before I give you some examples for this identity, I'm just going to give you one other task. And in that other task, you're just going to do this one. In the first thing which we did, our strategy was that to add them together in order to get rid of the second terms, because the second terms you can see that they are equivalent, they are exactly the same thing. That the sine beta cosine alpha and the sine beta cosine alpha from both terms, they are essentially the same, but I should say the sign is the opposite. That's why when you add them naturally together, the second terms are going to be vanished. But for the second case, for this case, our strategy is this, that we add them in a way together that the first term should be vanished. Can I do this like that? I just want to ask you, please do this. I said that I take sine alpha plus beta minus sine alpha minus beta. Please take a couple of seconds to see if this way you take this one, subtract this one from this, as I did. What is the end result that you get? Okay, what is the end result?
2 cosine alpha sine beta.
If I follow, that's right, but if I follow the same thing which I have right, you are exactly right, but I'm gonna follow the thing which I write, it becomes 2 sine beta cosine alpha. But the thing which you said also, this is absolutely correct because they are interchangeable. But as a result, I can just divide both sides and say that sine beta divide both sides by 2 then I get sine beta cosine alpha equals to 1 over 2 sine alpha plus beta minus sine alpha minus beta, which is going to be our fourth identity here. The fourth and the last identity. Becomes our fourth identity. Okay, look at this, guys. As you noticed before, I want to ask you a question. That is there any difference between the sine alpha cosine beta or sine beta cosine alpha? The variables alpha and beta are dummy. It doesn't make a difference if I say sine alpha cosine beta or sine beta cosine alpha. They are essentially the same, correct? Then it means that if you have a product which is sine alpha cosine beta, you can choose either of these two methods. Which one you feel more comfortable with. You can either represent that as a linear combination of the sine of the sum plus the sine of the difference, or the sine of the plus minus the sine of the difference, which it doesn't make any difference at all. You mean that this minus sign before and this plus sign before, it doesn't make a difference at all. Does it make sense to you guys?
Yes.
Okay. And now I'm going to give you one example in order to show that what do I mean. And then after we can go for the break. Okay, Gloria, when is your due date for your presentation of the project?
Yes.
When is your date for your presentation of the project?
Monday.
This coming Monday.
Yes.
Oh, interesting. Are you prepared for it?
Yes.
Oh, great. Okay, but please make sure that on Sunday night before you go to bed, please email me your PowerPoint presentation that I take a look into that to see if that's good for, and I just make some recommendations then. Okay?
Okay.
Thank you. Then as a very final example for today, you're going to cover this one. Cosine of 15x multiplied to the sine of minus 3x. Give it 1 or 2 minutes, please, to just find another way to represent the project. If I say that, okay, f of x is a function like that, write it as a linear combination of two functions then. Are you done now? Who's done? No one yet?
Almost.
No worries, take your time. I think we take 2 minutes, 2 more minutes that everyone should be done. Okay, shall I start?
Yes.
Okay, the thing which we learned before, the identity that we learned, what was that? It said that the cosine of alpha sine of the beta equals to what? It's 1 over 2 sine of what? Alpha plus beta minus the sine of alpha minus beta. That's the identity that we learned before. It's going to be identity number 4. This one. They can be the same thing. Now, based on this identity, if I want to apply my to f of x, then what f of x should look like? Becomes 1 over, oh sorry, 1 over 2 also should be here. Becomes 1 over 2, the sine of the sum of these two angles, 15x plus minus 3x. How much it gets to?
12x.
12x minus or plus 1 over 2, the sine of what? Their difference. You see? What is their difference? 15x minus 3x becomes how much?
18x.
That's right, becomes 18x. Then you will see that you can, by using those identities that you learned today, you can exactly start with a function which is a product of two trigonometric ratio and represent it and decompose it into, let's say, the sum, the linear sum of two functions then. And that's essentially that's what we learned today, and that's a good thing. And now, guys, I just want to ask you, please, go to your Desmos before we go to the break. We have 2 minutes. Go to your Desmos, plot this function to see that if you get to the right, I should say plot, you get the right plot. Go to your Desmos and plot them. And I'm going to do the same thing here on your Desmos. Share your screen with us to see what result did you get. Okay, guys, are you done with your plotting?
Not yet.
Please take your time. This is essentially very interesting that you see that there are many ways that you can decompose your trigonometric functions. Either you can reduce the powers, and you start, for example, the thing which we did yesterday, we started with, let's say, for example, sine to the power 6 of an angle, for example, x, and we decompose that into a linear functions of sine and cosine, which every individual ratio had power 1. It was so impressive. And now that's the second type of the decomposition. You start with a trigonometric function, which is a product of two ratios, and you decompose it in a way which is a linear combination of two other ratios. Depending on the application, that's interesting thing. Yes, Gloria and Philip, are you plotting the function?
Yes.
Okay, I'm gonna share my screen with you that you can see in the plots which I made. Okay. Guys, everybody sees my screen now?
Yes.
Yeah. Look at the first plot on the first one. I'm gonna activate this. What is this? This is a function that we were given. It is cosine of 15x times sine of minus 3x. And the plot is represented, the graph is represented in red, right? Now I'm going to take it off. I'm going to also have a plot of the function which we decompose that based on identities that we learned. They are the same function. This one is the decompose of this one, but the difference is that the first one is the product, but this one is a decomposition of this one based written on the linear combination. I'm going to write it. Look at that. It's this function which is plotted in blue. But the question is that if these two functions represent the same thing, the same function, the blue one is this, and if the red one also lies exactly on top of it, you see, it means that these two functions represent the same function. You see these two plots are matched together exactly?
Yes.
That's the red, that's the blue. When you have both of them superimposed, you see they are exactly on top of each other. You see that? Then
Yes.
it means that you have essentially two trigonometric functions which they are exactly representing the same reality to you. And that thing is we used by the decomposition that we learned. Any questions, guys?
No.
No? Isn't that beautiful?
Yes.
Yeah, that's so impressive. That's so impressive, really. That two functions, which they represent the same reality, and we know how to get one from the other one. Okay. When we come back from the break, we go the opposite direction. We go from the time that we have a linear sum, we want to find the products, the exact opposite direction that we took today. Then. Okay. Now the time is now, guys, it's 12:12. Please come back by 12:27. Okay.
Okay.
Awesome. Then see you soon in 15 minutes. Then. Okay, guys, are you back now from your break?
Yes.
Good. And then we can start to move on then. We are just gonna essentially touch on the very last identities that after this, which is gonna be today, we're gonna say goodbye to the trigonometric function, which I really like them myself a lot because they are so much fun to work with. But this is essentially the very last topic on the trigonometric function. Then I'm gonna put my laptop upside down. Then just start the lesson. Okay, now let's move on. Okay, now guys, in order to derive the strategy which we're gonna have for today is this. We say that in order to move on, I'm just gonna go back to the first identities that we drive. For example, this one. Before we go for the break, everyone is back. Just please say your name if you are there.
Rose.
Gloria.
Awesome, thank you. Guys, the thing which we did before we go for the break was that we started from the left to the right. We saw that we have a function, which that function is the product of two ratios in trigonometry. Then we were able to re-represent that function in terms of the linear combinations of the trigonometric ratio. And now, the thing which we want to do is going to be the exact opposite one. We assume that we have two linear combinations of the ratio of the sine and cosine, or cosine and cosine, or sine of cosine. We want to reverse back. We want to go back to represent the same function as a product of two ratios. Then that's the main map which we want to do it right now. Right now, we want to have the sum to be represented as the product. Okay, let's start with this identity. In identity number 3, you saw this identity, that the sine alpha cosine beta was essentially 1 over 2 sine alpha plus beta plus 1 over 2, you can factor 1 over 2 sine alpha minus beta. Do you remember this identity? That was a thing that we covered. Guys, everyone can see what I'm writing in terms of the light, the color of the pen?
Yes.
Is it everything clear?
Yes.
Awesome. Glad to hear it. We say that if that's going to be the product of the ratios, which is going to be the sine alpha cosine beta, and we represent it by this, I'm just going to make a change of variable. By the change of variable, what do I mean? I mean that, for example, imagine that Philip is there. I'm going to temporarily change the name of the Philip. Let's say call Philip, for example, Charlie. But it doesn't change the nature of who is Philip, but temporarily we're just going to rename Philip to Charlie or anybody else. And that's the thing which you want to do. I'm going to just call a variable. And that variable is going to be, let's say, for example, if I call this, let's say, if with the name of the variable, which I'm just going to choose, I say that, let me call this one. I say I introduce two variables. I'm just going to call my variables u. Let's call it u and v. I say u as a new variable plus v as a new variable. I assume that if I add them together, it gets me 2 times of the alpha. And also, I say that if I write u minus v, it gives me 2 times of the beta. That's something completely arbitrarily. You can just come up with any other change of the variables, but we say that we call that 2 plus u plus v becomes 2 alpha, and u minus v becomes 2 beta. U and v, they are new variables that I adopted. Then what's going to happen if I say, if I add them together? If I add these two lines together, what happens? I get 2 u becomes 2 alpha plus 2 beta, correct? Then as a result, if you divide both sides by 2, you get your new variable u is essentially what? Alpha plus beta. That's what we plan to do. We say that the alpha plus beta, it becomes my new variable. It becomes the first type of the variables which I'm going to get it from here. Then I say that based on the first equation which I have, the alpha plus beta, it represents u as a new variable. I say that I call the sum of the angles which I looked at as the variable u. And now, I'm going to come to say to something different. And I'm going to come to say, okay, what happens if I subtract these ones together? If I subtract these terms, I call that term 1. If I subtract it from term 2, what do I get? I get u plus v, which equals to 2 alpha, minus u minus v, which equals to 2 beta. Then you see that u, it becomes minus u, then v becomes plus v. Then what do I get? I get 2v equals to 2 alpha minus 2 beta. Everybody see what I'm writing?
Yes.
Then if I divide both sides by 2, I get v as a new variable is a difference of my angles, which it becomes my new variable, which I'm going to need it here. This one and this one are my new variables. Okay. Then you see that I can come here to the main equation which I had, and I write alpha minus beta as a new variable, which I'm going to call that v. Correct, guys? Okay, any questions, guys, so far?
No.
No? Then you will see that it is very crucial that you remember as a step that we took how to rename these variables. Always remember, you are given the alpha and beta, and u and v are the new variables that you are going to represent to the problem. Then you say that u plus v and u plus v equals 2 alpha, but u minus v equals to 2 beta. Then you can get what is u and what is v. And is it clear to everyone?
Yes.
How about Philip and Gloria?
Yes.
Yes? Right.
Yes.
Okay, now I have two variables now here. But the thing is that, guys, what if you go back to the identity, not the identity, the change of variables which I have written here. What is if u plus v equals to 2 alpha? What is alpha itself? Alpha is what? You divide both sides by 2, huh? Which is u plus v divided by 2, correct? Is it clear for everyone?
Yes.
Because you decided that the u plus v equals to 2 alpha, then you say easily that, okay, then the alpha is going to be, let's say, u plus v divided by 2. And the same strategy for beta. How much is beta then?
U minus V divided by 2.
That's so true. U minus v divided by 2. It becomes my new identity. Not identity, new expressions for the beta. I'm going to write it here like this. Okay. Now, we have now two expressions for u and v, and two expressions for alpha and beta, and all of them has been derived based on this crucial fact that you know that u plus v as new ones becomes 2 of the alpha, u minus v becomes 2 of the beta. Now, we are essentially done. I'm coming back to this one, to this example that we wrote. Starts from the same identity. I say sine alpha cosine beta was 1 over 2 sine alpha plus beta plus 1 over 2 sine alpha minus beta. And now, guys, the plan is what? The plan is that if I know alpha plus beta is going to be u, I'm going to write alpha and beta here in terms of the things which I derived. What is going to be the sign of alpha then? Becomes sine. What is alpha here? Alpha is u plus v divided by 2, correct? Becomes u plus v divided by 2 times cosine of beta. What is beta which I derived here?
U minus V divided by 2.
That's right, u minus v divided by 2 should equal to, I have 1 over 2. What is sine alpha plus beta? I have written here it's u, and you see here u is alpha plus beta. Becomes sine of u plus 1 over 2 sine of v. This is the end point of this identity. That by change of the variables, I was able to drive this one like that. Guys, you see what happens there?
Yes.
Is it clear for everyone?
Yes.
It needs some more practice, but the crucial thing is always remember, you have to always start from the products to sum, and always remember this identity, this change of variables is the key, the golden key in order to drive these ones. That u plus v becomes 2 alpha, and u minus v becomes 2 beta. If you change it to these kind of variables, then the things becomes automatic here and becomes very straightforward. Okay. Any questions, guys?
No.
Nothing? Okay. If you have no questions, how about Gloria and Philip?
No.
No? Then I'm gonna, if you have no questions, I'm gonna ask the question myself to you. Okay. Imagine that you have, let's say, I give you a function. For example, the function which I give to you is going to be this f of x is represented as the sum of the functions, which is going to be the sine of let's call that 12 pi x plus the sine of, let's say, call that 10 pi x. This is a function that we're going to start with. And what's the plan? The plan is that we are going to express that function in terms of what? In terms of the product of a function. I'm going to reshape the function, represent the function f in terms of the product of those two functions. Please, before I start, give yourself a couple of seconds to see what this plan is that going to be. I have the product, the linear combination of two functions. The plan is that write f of x in terms of the product of two functions as a kind of a representation, re-representation of the f of x. You please give yourself a couple of minutes, then we can retry it. Okay, anyone is done? Let me do this for you. Okay. I'm going to write the identity which I have. What the identity told me. You can drive it, or at this stage, you can simply, let's say, memorize it. What did we have? We had sine of u plus v divided by 2 times cosine of u minus v divided by 2 should equal to 1 over 2 sine u plus sine v. Everyone sees what I'm writing?
Yes.
Yes, nice. Okay, now the problem is that how do we start for this problem? Look at this one. I have the function which has been given to me. It's, give me 1 second, I drink some water. Okay, the function which is given to me here, in a sense, if you look at that, it's the sum, the linear sum of those two functions, which I have it on the right side of my identity here, which is that the sine u plus sine v. Then this is very reasonable if I come here and say I take 12 pi x and 10 pi x, 12 pi x as u, and 10 pi x as what? As v, correct? Because I'm going to compare the thing which I have here based on that. But they had to just have 1 over 2. They don't have 1 over 2. Then I will deal with that a little bit later. Then you see that, guys, if I had 1 over 2 on this side of this identity, it was exactly replicated by the one identity which I have here. Then I'm just going to subtract. Then I'm just going to multiply it by 1 over 2. And at the end, multiply that by 2. That 2 divided by 1 over 2, it becomes 1. And it shows that nothing actually has happened. But it was a kind of a trick to reconstruct the formulation which I have there. Then I'm going to rewrite this as this. Then in order to represent f of x, how do I write it? It becomes the sine. I'm going to rewrite the left side of the identity. Sine of u plus v divided by 2. If u this is here and v this is this, then u plus v, what is that going to be? U is 12 pi x, v is 10 pi x. You're adding them together.
22 pi x over 2.
That's right, 22 pi x divided by 2 times cosine of u minus v. Now you have to subtract them.
2 pi x over 2.
That's right, 2 pi x over 2. But remember, guys, in order to mimic the left side of my identity, I had to multiply this term to 1 over 2 to represent it like that. But at the same time, I have to multiply that by 2, which means that this one should be multiplied by 2. Then the impact is going to be 1. You see? Or you can say that you can just take this 1 over 2, multiply that to this side, then you had to put 2 over here. Then you will see that at the end, that your function f of x, which is sine of 12 pi x plus sine of 10 pi x equals to what? Equals to 2 times sine of 22 pi x divided by 2 cosine of 2 pi x divided by 2. That's the thing that we were looking for. You see that I just used the identity that we learned. In order to move backwards, it means that if I had a linear sum now, I turn it into a product of the function, depending on the application that you have. You can just use this manipulation and re-represent the functions in the trigonometry there. Okay, any questions, guys? Is it clear for everyone?
Yes.
Who said yes?
Rose.
Rose. Awesome. How about Philip and Gloria?
Yes.
For everyone is clear?
Yes.
Okay. Now I just want to give you one more example. Okay. Great. I'm going to give you this example that you do that yourself, please. Please start working on this. It's going to be a very easy one. I'm going to give you one example. The function is called g of x, which is a linear combination of sine of 14x plus sine of 6x. Please, based on the thing that you learn now, please write this linear sum into a product of two functions then. Okay, who's done now? No one yet?
I'm done.
Okay, thank you, Rose. How about Philip and Gloria?
Not yet.
Not yet, okay. I was planning to take Friday, a very easy day for the lessons which we have, but it turned out the last day, the Friday, it had lots of identities to learn. Sorry, guys. Okay. How about you, Philip? Are you done? Oh, Philip is done. Gloria, are you done?
Yes.
Fantastic. Let's do that together. We know the identity. The identity is what? The identity is this. That we know that I'm going to multiply 2 to the other side. We know that this 2 times of the sine of u plus v divided by 2 cosine of u minus v divided by 2 should equal to sine u plus sine v. Then if you compare the left side of your identity, you see that then as a result 14x can play the role of the u and 6x can play the role of the v. Then as a result, you can represent g of x by mimicking the right side of this identity, which becomes 2 times of sine of u plus v divided by 2. 14x plus 6x divided by 2 becomes how much?
10x
That's right, divided by 2 times cosine of 14x minus 6x divided by 2. Or g of x becomes 2 times of the sine. I'm going to simplify that. 20x divided by 2 becomes 10x times cosine of 14x minus 6x becomes 8x divided by 2 becomes 4x, correct? Then you will see that at the end, we were able to represent your g of x from a sum of the linear functions into the product of two functions then, correct? I'm going to give you more exercises like that for your homework for this weekend. Then no worries. If you have some problems, you can have more practice. And in case if you have problems, always during the weekend, ask me questions by posting your questions on the Schoology website. I give you the answer right away then. Okay?
Okay.
But any questions for this one, guys?
No.
No? Everyone is fine?
Yes.
Yeah? Okay. Glad to hear it then. Then guys, there is not much to be done except two things that I have to remind you. The first thing is that please stay tuned for your homework. There's lots of homework to do. Then please, as soon as you get your homework from me, start working on it. Then you have to email it to me before the class on Monday. Don't forget that. The second thing is that, Gloria, your presentation is Monday, huh?
Yes.
Yeah? Please don't forget to just email me your slides on Sunday night then, okay?
Okay.
Fantastic. Good luck preparing for your for your presentation. And then if nothing's more to be done and no question if you have, then I see you on Monday then. Then have a nice day.
You too.
Bye, everyone.
Okay.
Bye.
Goodbye.
Bye. And also, Rose, for you, I'm going to send the links to the things that we saw today on the Schoology website. You can see these kind of videos on how to prepare for the math modeling challenge then.
Okay.
Awesome. Awesome. Thanks, everyone. Have a nice weekend. See you all on Monday then.
Bye.
Take care. Bye, everyone. Goodbye. Goodbye, Rose. Have a nice day.
Goodbye.
Good luck with the math modeling challenge next week then. I'm going to help you. At any question, I'm going to help you, but it's good that we work as a team then.
Okay.
Awesome. Enjoy the weekend and see you Monday then.
Bye.
Thank you. Take care, Rose. Bye-bye.